Hello, we are the Colder team, or Categorization of Lunar Deposits-Regolith. I'm Alex Konyk. Joining me virtually are Paul Granda, Paul Dinh, and Avery Romanoli. So a little bit of background on our project before we get started. NASA has committed to returning to the moon. Not just returning, but staying there, in the form of a lunar base. The cost to reach the moon and to deliver 1 kilogram of resources is approximately $1 million. This is a lot of money, and for a lunar base could cost billions. What we want to do is we want to find some way to offset this cost. But these resources are hidden. They're not close to the surface. So what we've committed to doing is creating some sort of analyzer that will take samples from different locations, here the moon, hence lunar, and analyze them for different material properties, different elements, and above all, ice or water. On the moon, there are these things called PSRs, or permanently shadowed regions. These permanently shadowed regions are always dark. They are built in such a way that the sun never touches them. So this could mean a rock that's located near a pole that has a shadow around it all the time. This could be craters, and inside the craters are ice crystals, potentially. What our project sets out to do is to find these resources and categorize them and put locations to amounts and try to map these resources so that when it comes time that we need liquid water or we need to hydrolyze it into hydrogen fuel and oxygen, that we can find these resources and get them for a fraction of the price. So our project is to analyze and to find and to categorize. So now let's hand it off to Avery Romanoli to see how this whole thing works.
I'm going to do a walkthrough of the full CAD assembly. So here we have the entire assembly in SolidWorks, and I'll start with the carousel assembly. So this is mainly just a plate and a base, and this top plate retains 5 sample containers, and it spins by this shaft here, which is rotated by this stepper motor retained at the bottom of the base. The reason for this design was so that the drill could have clearance to drill into the regolith, and then also allow for easy collection of the sample from the drill. So this allows the sample container to be rotated once the drill has picked up the sample, and then shake the sample into the sample container. From there, the plate will rotate the sample, whichever one is looking to be analyzed at the time, and this gripper jaw assembly can move down the rail to pick up whichever sample container. And for the gripper jaw assembly, it's made up of a few different linkages attached to this base plate, and then a stepper motor comes up through the bottom here and rotates this component, which then rotates the rest of them. Works like this. And this mating surface here is so the sample container can be retained easier and allow for the clearance for the sample container to actually be retained by this chamfer here. And it will actually lift the sample container out as it grips the sample container. And then from there, once the sample container is retained in the jaws, this entire assembly is moved by this second stepper motor here, which rotates this gear and transports the entire assembly down this track. And I made this transparent here so we could see how the bearings allow for very smooth movement up and down the rail. And once this comes down to this ram assembly, so we can get some mechanical properties of the soil, see how this ram can move up and down. And then there was going to be a mass sensor or load cell in this ram platform, so we could collect some properties. I made this part transparent here so we could see how this ram rides along these two bearings, and this gear drives the ram up and down, actuated by that stepper motor on the front of the ram system. There was also going to be a rotating component here to allow for a very smooth transition from the sample container up onto the platform, which then the gripper's jaws would open up so that there wasn't unnecessary force being put on the gripper jaw assembly while it was in testing. From there, after the sample's analyzed, it can come back to this sort of middle position, and then this entire rail can rotate up and over, driven by this stepper motor here on back of the isogrid panel, and driven by those two gears, so that the soil can be disposed of and the sample container can be used again. From there, it rotates back, all the way down the rail, places the container, opens the jaws, and then waits for another sample to be tested. This isogrid panel originally was going to be an actual isogrid panel that's used commonly by NASA, but for the prototype we just adjusted the thickness of this material so that would provide the same amount of stiffness if it were an isogrid panel, rather than us machining one ourselves or buying it. Most of these components are made out of aluminum 6061 plate that we cut a lot of the pieces out already. We drilled the holes for the rail components, and the sample container was going to be made out of a tube that we would then have to attach these retaining collars and supports. And that about does it for the function of this assembly. Thank you.
With the CAD assembly perfected, we had to now work on controlling the system. Now, unfortunately, due to the COVID crisis and the university's policy, we were unable to prototype this, but we were able to do the next best thing, which is create the flow of logic on how these systems are going to interact with each other, different errors that could occur, and how we are going to really plan out the whole thing. So, without further ado, here's Paul explaining the whole process.
Now, let's talk for a minute about a control system. The purpose of a control system in our design is to translate user input into a very specific set of commands relayed in sequence to each of the motors within the design to accomplish a set of very specific tasks. Let's take a look at that now. So, what you see here is a hierarchy of command structure in the form of a flowchart for the control system. You're always going to start this top command input block. At this point, the system is in a standby state, waiting for commands in order to accomplish the user's tasks. We've broken down the conceivable number of tasks that this system is meant to accomplish into 4 basic categories, plus 1 extra in order to capture any sort of unexpected out-of-scope position adjustments that we might need to make. So let's break down these individual commands. This first command is the acquisition command. As I stated before, all the motor data is fed in, the system knows where it's at, starts from a default, and then when it receives or wants to move to a position, it's going to update that information back into the database. So it moves the sample to the top of the carousel, and the position data of that motor is updated inside the database. This is stored later, able to be accessed for subsequent operations. It's going to move the jaws, update the data, open the jaws, update the data in the database, rotate the rail up, down, update that data, and then here at the closing of the jaws, we have something different. We actually have data flowing in the opposite direction. We have the command structure accessing the database and seeing where the jaws are at, where it needs to be. By keeping track of where the jaws are and where they need to be, you can actually just reverse the operation. Go back the same number of steps that you went forward, and you'll end up in the same sort of place. This is very useful in keeping high fidelity tracking of the position and not having to have so many sensors involved in locating the actual component. Second command is a little bit different. It starts the same. Testing a sample, all of the data is read in by the command system. It knows where it is. It moves the sample container over to the testing area, updates that position. Then the RAM test system, that motor steps forward by 1, logs the position, then it's going to check the data on the load cell. We're aiming for a very specific sort of compression here. We're aiming for 50 newtons of compression in order to accomplish the test. So we're going to actually have a decision block down here. So the data from the load cell is read in and compared to this 50 Newton sort of limit. If it has the 50 newtons has been reached, then we're going to move on to next. If not, however, we're going to be fed back up into the operations chain. The motor is going to be stepped one more time, the data logged, we're going to recheck and keep doing that cycle until we reach the actual value that we want to reach. Once we're there, we've known that the test is complete. We know how far the system has traveled. We know what the force is on it. We can use that information, that useful data, to calculate and extract the scientific information from the sample. After that, we'll simply reverse the RAM, undoing what we've done before using the same position data for that motor, and then we're finished. Now, let's say after you test it, you want to dispose, get rid of the sample. So again, you're reading all the data, you know where you're at. You move the sample to disposal point by taking the difference between the current position and the desired position, update the information, rotate the rail, dispose of the sample, and then you'll rotate back, again simply reversing a previous operation, knowing where you've been, where you want to go, taking that difference. At the end of it, the data will be updated in the position database, and you're ready for next. Let's say you don't want to dispose of the sample, you want to store the sample. This command is basically a simple reversal of the entire acquisition command. It's very similar. I won't go into it in detail.
Now I would like to talk about the materials. Our design will operate under extremely cold temperatures, expected to range at lower 20 Kelvin. We also want to limit the weight of our design as low as possible, because the cost to deliver it to the moon is very expensive. It's about $1 million per kilogram mass. Because of that, we decided to use aluminum 6061 T6 for the main body structures to reduce weight and make sure the system must be robust enough to deal with the hostile environments. Aluminum is also commonly used in spacecraft structures. The material was selected for its mechanical performance properties, such as coefficient expansion, high strength-to-weight ratio, and adherence to the off-gassing requirement as specified by NASA. The reason we employ off-gassing standard is to limit the possible contamination from materials. We also used stainless steel for fasteners, thread inserts, and probe subject to heavy wear because stainless steel is available, low cost, and strong corrosion resistant. It also meets NASA off-gassing standards. During ordering, we had to go back to order different size of the screws because we changed the size of our plates and we learned new things. We also ordered different inserts. We ordered lock-in versus non-lock-in inserts. We want a non-lock-in insert for just assembly, and we plan to use the lock-in insert later for the vibration test. We also used PLA plastic for rapidly prototype to verify interfaces and mobility of components. This material allows for low-cost prototyping, which is essential to ensure the intended design works as intended before further, more costly prototypes are produced. I would like to talk about our project's budget. Our team is self-funded. We didn't have any money to order any parts before we got funding from Boeing and Botstiber. For Boeing crane, we submitted our proposal and got $500. We used the crane to place our first order. For Botstiber competition, one of our team members had to take an online program to learn about entrepreneurship for engineers. Then we had to write an essay to describe how our product would be sold to the market and describe the work we accomplished to validate our ideas regarding market viability. And finally, we had to present it in person. The competition helped us learn how to change the pitch from senior design to business perspective. Because we were pitching to business people rather than engineers, we had to present it differently. Eventually, for this competition, we won the right to spend up to $2,000 on our project. And now let's look at our props on the list. This is the first order from Boeing crane. We ordered some aluminum plates, low cell, thread inserts, washers, and some screws. We spent $497 out of $500 in this order. And this is the second order from Botstiber competition crane. We ordered some more different style of aluminum bars, aluminum plates, gears, rack, and bearings. We also ordered the power supply, the control panel, some more fasteners, and we ordered stepper motors and lunar soil. Totally, in the second order, we spent $1,238 out of $2,000.
Now, we couldn't actually do anything with these materials, which was very unfortunate, but we did the next best thing, which was leave them with our advisor so that he could give them to the next set of researchers, the next people who were going to further this project. But we had a full testing plan set up, and for that, I'll give you over to Paul.
We had several benchmarks for our product. So the first of which was mass. We had a hard 15 kilogram limit imposed by NASA on the lander payload. We were going to weigh the prototype, see how it compared to that limit. We had parts that we were not able to manufacture to a final shape due to the complexity or the cost involved with that. We would have used estimates from SolidWorks mass properties in order to account for this and give us a good idea of where we needed to go. We would have also conducted thermal and vibration tests, approximating the conditions on a rocket launch and transit in and out of the sun. We had connections to the U.S. Naval Research Lab. We would have used their facilities as well, making a trip and taking the prototype with us. After the test, we would have inspected it, see if any fasteners came loose, if there are any obvious signs of wear. We also had a fatigue test lined up. We purchased lunar soil simulant that had the same exact physical properties, and we would have seen how well it operates when it gets onto the moving parts, how well the individual parts were shielded from dust, and what improvements could be made without adding too much weight and pushing us over that limit.
So now comes time for reflection, to look back and see how much our team got out of this project. And talking to our team members, it was actually a lot. We got to work through design processes iteratively. We got to see what worked and, well, what didn't. We got to figure out virtual connections, so looking into FEA analysis and look into some Simulink. We got to establish different contexts. We talked to a lot of different people, both in the university and outside the university, and we had people at the Naval Yard looking to test our project for vibration and thermal in their thermal testing chambers. So a lot of people come into senior design and they leave the projects afterwards where they fall. And that's really sad to me because our project has a lot of future. And in talking to Dr. Yousuff, we are embracing that future. We've left all of our parts with him. We've talked to different senior design teams, different STAR program scholars that can take over and really work through this design and use it as a baseline for what exactly is going to happen. So if this is going to be our senior send-off, then it was a good one and it was a pleasure. So thank you so much, and I hope this was good enough.